Hello, my name is Unice Anne C, and I will explain the relationship between magnetism and electrical current. But first, we must know what these terms mean.
Magnetism is a force of attraction between ferromagnetic metals and a force of repulsion between diamagnetic materials. There are various kinds of magnetism, out of which ferromagnetism is the strongest type. Ferromagnetism gets its name from the word ferrous, which means iron, which was the first metal known to show attractive properties to magnetic fields. Most of the ferromagnetic materials are metals. Common examples of ferromagnetic substances are iron, cobalt, and nickel. Besides, metallic alloys and rare earth magnets are also classified as ferromagnetic materials. Magnetite is a ferromagnetic material which is formed by the oxidation of an iron into an oxide. It has a Curie temperature of 580 degrees Celsius. Earlier, it was recognized as a magnetic substance. Magnetite has the greatest magnetism among all the natural minerals on Earth. Ferromagnetism is a unique magnetic behavior, or a phenomenon where materials attain permanent magnetism, or they acquire attractive powers. It is also described as a process where some of the electrically uncharged materials attract each other strongly. Diamagnetic materials are those materials that are freely magnetized when placed in a magnetic field. However, the magnetization is in the direction opposite to that of the magnetic field. It means that the materials are usually repelled by a magnetic field. Electrons in an atom revolve around the nucleus, thus possess orbital angular momentum. The resultant magnetic momentum in an atom of the diamagnetic material is zero.
Some of the most common examples of diamagnetic substances are copper, zinc, bismuth, silver, gold, antimony, marble, water, glass, and sodium chloride. A magnet displays the properties of magnetism. Magnets occur naturally, such as the mineral magnetite. An electromagnet can be made by coiling insulated wire around an iron core and running current through the wire by connecting it to a battery as shown. A simple magnet has two poles, a north pole and a south pole. A free-hanging magnet within the Earth's magnetic field will orient itself longitudinally between the Earth's poles. The magnet's north pole will face the Earth's north pole, and the magnet's south pole will face south. If you've ever played with magnets, you'll probably notice that when like poles of the magnets are facing each other, the magnets will repel. But hold two unlike poles together, they will attract. Here's why all magnets have something called a magnetic field. Magnetic fields are invisible and surrounds the magnet, causing a magnetic force. This is what causes magnet materials and magnets to either attract or repel. Even though magnetic field lines all have the same strength, the strength of the magnetic field is greater the nearer to the magnet. It's because the field lines are more concentrated, increasing the overall strength of the magnetic field. There are two different types of magnets: permanent and induced. Permanent magnets are always magnetic, meaning that their magnetisms can be turned off, whereas induced magnets aren't always magnets. They are unmagnetized most of the time. But when placed inside another magnetic field, it acts like a magnet and attracts. Magnetic materials like iron and steel can be turned into magnets. If you placed an iron paperclip close to a permanent magnet but without touching it, the paperclip will become an induced magnet with the end nearest to the magnet having the opposite polarity of that of the magnet. Because the paperclip is now an induced magnet, we can add another paperclip to it and another paperclip. Remove the first paperclip of the magnet and all paperclips will lose their magnetism. As was said by the previous reporter, in both classical and modern theories, electricity is the movement of subatomic particles, which are electrons or charged particles, that is attributable to the existence of a charge. A flow of electric charge through a conductor is an electrical current or simply current. Imagine it being like water in a river carrying energy. The electric charge in the electrons causes resistors in light bulbs and electric fires to heat up. It also creates magnetic fields in motors, inductors, and generators. A strong link exists between electricity and a magnetic field. The force of a magnetic field can produce electrical current flow in a conductor. On the other hand, electrical current flow in a conductor produces a magnetic field. Thus, electromagnetism is the interaction of these two important forces. Electromagnets are incredibly useful. They can do all the things a normal magnet can do, but can also be switched on and off. Electromagnets have many uses, from moving cars in a scrapyard to high-speed maglev trains. The trains are suspended above the rails by strong electromagnets, reducing friction between the train and the track. There are other uses as well. When a current flows in a wire, it creates a circular magnetic field around the wire. The strength of the magnetic field is greater when it's closer to the wire. If the current is increased, or by adding a core that is made of magnetic material and wrapping the wire around it, this is known as a solenoid. The magnetic field around a straight wire is not very strong, and so coiling the wire around an iron core creates a stronger electromagnet. This is sometimes known as a solenoid. We can use an iron nail to create a simple electromagnet. The strength of the solenoid electromagnet can be increased by increasing the number of coils or increasing the current. The more coils, the stronger the electromagnet is, and so the more paperclips you can pick up.
When a conductor is moved through a magnetic field or a magnetic field is moved across a fixed conductor, a voltage is produced in the conductor. The voltage causes current to flow through the conductor. When this happens, current flow is induced in the conductor, and the phenomenon is called induction. Moving the conductor in one direction across the magnetic field causes current to flow in one direction. Reversing direction of conductor movement reverses direction of current flow. When the conductor is no longer moved through a magnetic field, current flow stops.
When a constant voltage is applied in a closed circuit, the voltage forces current to move in one direction to the conductor. As current flows in one direction, the magnetic fields of the electrons or charged particles align and combine to produce a strong magnetic field that extends around the conductor. Increasing voltage and thus increasing current flow produces a stronger magnetic field. Decreasing the voltage and thus decreasing current flow reduces the magnetic field. When the circuit is opened, current flow through the conductor stops, and the electrons or charged particles moved in random paths, canceling their magnetic fields. With no current flow, there is no magnetic field surrounding the conductor. Finally, if the connections of the conductor to the power source were switched, the polarity of the circuit would change. Current would flow in the opposite direction, and the polarity of the magnetic field around the conductor would reverse. These are the sources I used for my report. Thank you for listening.